So this presentation is going to be about the trends in the periodic table, or what I commonly refer to as periodicity. So we're going to start out by watching a short little video.
There are 92 naturally occurring chemical elements, or atoms. They differ in the numbers of protons, neutrons, and electrons they contain. The periodic table arranges these elements in order of complexity. For example, hydrogen, element 1, is the simplest atom because it contains only one electron and one proton. It appears at the top left of the table. Unquadium, at the other end of the table, is the most complex, with 114 protons and 114 electrons. The number of protons in an atom is the same as its atomic number. The atomic number for each element appears just above its letter abbreviation. The periodic table also arranges elements together in groups, or families. Elements in a vertical column are called a group. The elements in a group have similar chemical properties. For example, the noble gases on the rightmost edge of the periodic table have great stability and limited reactivity with other elements. Group 1, the alkali metals, have similar reactivity. They readily form hydrogen gas when added to water. A horizontal row of elements forms a period. The differences between elements in a period and elements in the next period are consistent between the groups. For example, if we look at the difference between elements in group 18 and in group 1, we see that the difference in atomic numbers is constant. 8, then 8, then 18, then 18, and then 32. This means that the atoms are consistently becoming larger by a set number of protons as you move from period to period. Note that there is a special block of elements below the main table known as the lanthanide and actinide series of elements. They are grouped together and placed below the main body of the table to keep it from becoming too wide. Elements with atomic numbers greater than 92 do not occur naturally, but can be produced in laboratories. Most are not very stable and decay rapidly.
So there's a little synopsis of what the periodic table is all about. So let's start talking about the trends in the periodic table. So the main trends that we're going to talk about is the idea of atomic radius, which I will sometimes refer to as atomic size, ionization energy, electron affinity, ionic radius, and electronegativity. So we're going to start with the most important one of them all, which is the atomic radius, because if you can understand atomic radius or atomic size, life will be so much easier in understanding all the other trends. Okay, so what is the atomic radius? By definition, the atomic radius is half the distance between the nuclei of identical atoms that are bonded together. So you can see a picture here. They have two chlorine molecules, and they measure the distance between the adjacent nuclei. And what they do is then they take that distance and cut it in half, and they can get a rough idea of basically how large the atom is, where the furthest electrons are located. So what is the trend for atomic radius on the periodic table? Well, first we need to discuss the idea of energy levels. So on the periodic table there are 7 periods. And each time you move down to another period, the electron is further away from the nucleus. And remember, if the electron is further away from the nucleus, it has more energy, like the idea of the concentric circles of the Bohr model of the atom. When the electron is further away from the nucleus, it means the atom is getting larger. This is because of an increase in the shielding by the electrons closer to the nucleus. Now, it's different as you move across a period. Don't forget, this is going from left to right in the rows of the periodic table. As you move across a period from left to right, the number of protons is increasing, along with the number of electrons. So if the nucleus is becoming more positive and the electrons are entering the same relative distance from the nucleus, the atom is actually getting slightly smaller. So, and the reason is because the shielding is constant. So let's take a little look at a graph that might help give you a better visualization of this. So you can see here that this graph blocks it apart by both periods and groups. So let's notice for group 1 first. Look at hydrogen, and then look at cesium. That's a group, and that's group 1. Now as we go from hydrogen to to lithium, to sodium, to potassium, to rubidium, to cesium, you will notice that the size of the atom is increasing. That's going down a group. But if we take a look at the period, let's say starting at lithium and going across all the way to neon, you can see that the size of the atom is slightly decreasing each and every time. And that's because of the addition of a proton and an electron. And what that does is it actually makes it so that the atom gets slightly smaller because the electron is entering the same energy level, meaning relative distance from the nucleus. And again, for those of you who don't like a graph, here's a general trend. And this would be a great thing to write down and have in your notes. So you can see for atomic radius, as we go down a group, the atomic radius increases. And as we move from left to right across the periodic table, across the period, the atomic radius decreases. Now, there's this case in which we can lose or gain electrons, and this is what we call an ion. It's no longer called an atom because now there's a charge associated with it. Okay? And atoms that lose electrons are called cations. Okay? Not cations, they're called cations. Now, the way I remember about cations, think about it. If you lose electrons, you're becoming more positive. Okay? Losing electrons are negative, so if you lose electrons, you're becoming more positive. Well, the way I remember this is I think of cats. And I think cats, oh, they're soft, they're fluffy, and they're great little animals, so those are positives. Atoms that gain electrons, meaning gain more negative, are anions. And the way that I think of it is that they're like, well, anions kind of remind me of the word onions. And when I cut them for cooking, they make me cry. So let's watch a short little video on the idea of anions and cations and the idea of ions.
An ion is an atom, radical, or molecule that has gained or lost one or more electrons and has a negative or positive charge. For example, when a sodium atom loses an electron, it becomes a sodium ion. Sodium ions have a positive charge. Other atoms become ions by gaining an electron. For example, when a chlorine atom gains an electron, it becomes a chloride ion. Chloride ions have a negative charge.
Okay, so we can see the difference between them. Now the trend for ionic radius is exactly the same as that of atomic radius. So as we go down a group, the ionic radius is increasing, and as we go from left to right across the period, the ionic radius is decreasing, both for cations and anions. So now let's talk about the next one, which is ionization energy. So before we can do that, we need to have an understanding of what ionization energy is. It's the energy it takes to remove an electron. The energy it takes to remove an electron. So remember this, the size of the atom as we go down a group gets bigger. So if the atom is getting bigger and the electron is further and further away from the nucleus, meaning the force of attraction between the protons and electrons, what ends up happening is it takes less energy to remove the electron because the electron's further away from the nucleus. Remember, that's what's holding the electron nearby. So as we move down the group, the ionization energy decreases because the atom is getting bigger. Now, as you move down across a period, the ionization actually is increasing. And this is because the size of the atom is getting smaller. The smaller the atom, the more energy it takes to remove the electron. So if you look at this graph right here, you can see the trend. As we go across a period, the amount of energy it takes to remove an electron becomes much, much greater. But as we go down a group, the amount of energy it takes to remove the electron gets smaller because of the fact that because the atom is getting bigger, that the energy, it takes less energy to remove that electron. Here's a summary picture of what we're talking about. Ionization energy decreases as we go down a group, and the ionization energy increases as we go across a period.
An ion is an electrically charged atom. If the ion has more protons than electrons, it is a positive ion or cation. If it has more electrons than protons, it will be a negative ion or anion. Ionization is any process that causes a gaseous atom to become electrically charged. A sodium atom is ionized when energy is added to remove an electron. The amount of energy required to do this is called the ionization energy. Ionization energies differ among atoms. This table shows the ionization energy required to remove the first electron from an atom. Once an electron is removed from a neutral gaseous atom, the atom becomes positive, and its remaining electrons are held more tightly to the positive nucleus. Additional ionizations to remove a second or third electron require increasingly more energy. A gaseous atom can also ionize by gaining electrons. Most atoms release energy in this process. This energy represents the atom's electron affinity. Electron affinity can be thought of as the tendency of an atom to accept electrons. Atoms with high electron affinities tend to form negative ions more easily than those with low electron affinities.
Okay, so they introduced the idea of electron affinity, and that's what we're going to talk about next. So electron affinity is the ability to gain electrons, and when that happens, they basically release energy. Now, the way affinity means to love or be very attracted to. So the trend across the periodic table is usually that there's an increase in electron affinity as we go across a period. And the reason being is that if you think about it, on the far right of the periodic table is the noble gases. And the noble gases are the ones that are the most stable with a certain number of electron number. So therefore, every atom is trying to achieve that noble gas electron number. And so as we move across the period, the electron affinity increases, meaning the love for another electron increases. As we go down a group, however, because we're getting more and more electrons, the actual amount of energy that it takes, or the electron affinity, is decreasing. And this correlates again with the size of the atom because it's getting bigger and bigger and bigger. Here's a general trend again. So electron affinity as we go down a group decreases, and as we go across a period, it increases. You can see the colors there. And look at the ones that are right next to the noble gases. There's a huge increase in the amount of energy. And this leads me to the last one, which is electronegativity. Now, electronegativity is kind of a weird one. It's similar to electron affinity, but slightly different. So this is the tendency of an atom to attract electrons when they are chemically combined with another element. Now, there is one element that is the most electronegative, and that's fluorine. I consider it to be the bully on the periodic table. That's why I have Buford there on the right-hand side from Phineas and Ferb. And so fluorine is one of the most electronegative, has the highest ability to attract electrons when it's combined with another element. And basically everything pales in comparison to fluorine. So as you move away from fluorine in any direction, the electronegativity decreases. And here is a picture of it. You can see it with the very dark colored region for electronegativity where fluorine is located. And as we go down a group, it decreases. But as we move from left to right across the periodic table, it increases. Or if you want to look at it from the fluorine standpoint, as you move from right to left, it's decreasing in all directions.
Electronegativity is a measure of the ability of an atom in a chemical compound to attract electrons. It is measured on an arbitrary scale of 0 to 4, developed by Linus Pauling. Fluorine has the strongest ability of any element to attract electrons from other atoms. For elements in the same period, the ability to attract electrons decreases as the number of filled orbitals decreases. The hydrogen atom has only one electron. It is almost equally likely to attract from or give up electrons to other atoms. As atoms get larger, the distance from the outer electrons to the atomic nucleus increases. The ability of these atoms to attract electrons to their outer orbitals decreases.
So you can see, again, the idea of atomic size plays a role in all of these. So here's a general trend of what we just talked about today. Okay, is the idea of the shielding, atomic radius, ionic size, ionization energy, electronegativity. All right.